Good evening, everyone. Welcome to the 17th weekly session for NPTEL GATE series. Today, we'll be looking at some concepts in permeability and seepage, and also some previous year problems. So I've selected about 5 to 6 problems from GATE 2018 to 23. So these topics might have been covered earlier. So maybe we'll spend more time on the problems. But anyway, I'll be explaining whatever concepts are required for solving the problems, right? So uh, before we get started, if there are any doubts, you can ask. Are there any doubts from previous class? I don't see anything in the forum this week. So
No, sir.
okay. So okay, then we'll get started. Yeah, there is nothing. So welcome once again to today's session. Uh, So we were last in the last session we just got started with hydraulics of soils, how soil interacts with water, what are the different problems that arise. So let me. So typically, as I said, we have three types of problems in the interaction between soil and the water that percolates. First, when we try to estimate the amount of. So the first class of problems is about estimating the amount of loss from dams. So say how much quantity of water percolates to the soil and comes out. So that is dealing with seepage. The second class of problems is suppose we take a saturated soil and we load it. Under the action of the applied loading, the soil will the water in the pores of the soil slowly drain out if the permeability is sufficient. So it will slowly drain out, and the soil will become the particles will get arranged closer and closer. So this under the action of an applied load, soil gets compressed slowly, and due to water draining out, the porosity decreases, and this is called consolidation. So this is the other. So when we deal with so consolidation is important from the aspects of settlements of structures, because as water drains, uh, we have the structure going down. So it is important from settlements, and as water goes out, the interaction between soil particles is also stronger for some reason. So it also deals with the strength of soil. So with consolidation, the strength is typically increased. And there are certain other, and it is also important for the rate of drainage. How long it takes for settlement. So this comes under the topic of consolidation. And the other important area that arises in the case of design of dams is stability. So there are various failure modes of dams that arise just because the water percolates through the soil. So it can be due to uplift pressure, it can be due to piping failure. So that is the other class of problems we encounter in hydraulics of soil. So Uh, so all of these phenomena are governed by what are called the hydrodynamic equations. And if you remember in the last session, we considered a small cubic element of soil. With suppose this is x-axis, this is y-axis, and this is z-axis. It has dimensions of dx, dy, dz. And if we take any one plane, suppose we are looking from the top, I said this will be the projection of the element onto the xy plane. So this is just dx, dy. At the center, we have velocity vector v. And this velocity vector is called the discharge velocity of. the fluid through the soil. And what is the discharge velocity? So as I said, okay, we'll come to it. So this discharge velocity, is, since it is a vector, it has three components: Vx, Vy, and Vz. Then what did I say? So suppose the velocity, the x component of velocity is Vx at the center, and suppose this point is, say, point x comma y. The point on this face will be x minus dx comma y, and the point on this face will be x plus dx by 2. The entire length is dx, so x plus dx by 2 comma y. So using the Taylor's expansion, we saw the velocity, the x component of the discharge velocity at this point will be nothing but, if you use the Taylor's expansion, it is Vx minus partial Vx with respect to x dx, and it will have certain dx by 2, and it will have certain higher order terms, which of the order dx square. And on the right hand side, so this is, say, Vx left, and Vx right is Vx plus partial Vx with respect to x dx by 2 plus higher order terms. Now, if these are the discharge velocities, the flow rate on the left face in the x direction is nothing but the velocity multiplied by the area. So the area of this cross section is nothing but, so this area is dy multiplied by the thickness into the plane is dz, which is the same on the other side. So the flow along the x direction is nothing but Vx on the left face. What is the volume that is flowing into the mass of soil? It is Vxl into area. So it is nothing but Vx minus partial Vx with respect to x dx by 2. We can neglect the higher order terms, multiplied by dy dz. And similarly, Qx on the right face, we saw it is Vx r times a. It is Vx plus partial Vx with respect to x dx by 2 dy dz. What is the net outflow? So the net outflow of water through this volume of soil is Qx, which is outgoing minus incoming. And what is that equal to? So Vx gets cancelled. It is nothing but partial Vx with respect to x dx dy dz. You have a plus dx by 2, minus of minus dx by 2 will become plus dx. So this is in one direction. Then what did we say? We saw that the net flow out of the mass of soil is along x direction plus whatever is flowing along y direction plus whatever is flowing along the z direction. Now this is what is Qx? So it is partial Vx with respect to x dx dy dz plus, similarly, if you do a similar analysis, this will become partial Vy with respect to y dx dy dz, and this will be partial Vz with respect to z dx dy dz. So this is the volume of water that is flowing out of this small cube every per unit time. So if so much water is going out, it means the amount of water inside that cube has to decrease by the same magnitude. So so what is the volume of so we assume that the soil is in saturated conditions. So if the soil is saturated, what does it mean? All the pores are filled with water. There is no air. So if you remember the three-phase diagram, you have soil and you have water. There is no air. The volume of air is 0. So the volume of water is nothing but the porosity into the volume of soil, the entire total volume. What's the total volume? It is dx dy dz. And suppose eta is the porosity. This is the volume of water. Now it is decreasing. So if this is the net outflow, it should be equal to minus the rate of change of the volume of water inside that cube. So here finally we have the equation as partial Vx with respect to x, as partial Vy with respect to y, as partial Vz with respect to z, into dx, dy, dz is equal to minus of d by dt. What is VW? It is porosity into dx, dy, dz. So this is what is called the continuity equation. This forms the basis for all problems, whether it is seepage or if it is consolidation. So this is called the continuity equation. Basically, it is law of conservation of mass, continuity equation. So now, so this is the general case. So we have already written what is the continuity equation. Now for this particular case of steady state seepage. Right. So what is steady state? Whenever we say steady state in fluid mechanics, you know it is the time derivatives is 0. If something is not changing with respect to time, we say the system is in steady state. Now, if the flow through soil is in steady state, the right hand side is 0, and dx, dy, dz it's just an infinitesimal volume, so it is not equal to 0. Therefore, under steady state seepage in 3D, the continuity equation becomes partial Vx with respect to x plus partial Vy with respect to y plus partial Vz with respect to z is equal to 0. So this is called the continuity equation under steady state seepage in 3D. But typically, the conditions that we encounter in civil engineering applications are not 3D. So if you have a dam, we have a dam like this. It is built across the river usually, so it is very long. So if the length into the plane of the dam is say L, and the dimensions in plane are say dx and say dz, usually dx dz is much less than length. And say the dam is supporting water table this side. Uh, uh, this length is very long, so you can assume things to be under planar flow. That is, the water seeps through the soil. So there is soil here. Water seeps through the soil below the dam to the other side because soil is permeable. Soil is not like, it's not a rubber sheet, so it is permeable. Therefore, water seeps through this. But since the dam is so long and the water table is, the water level is almost the same throughout, there are no changes in elevation or anything. There is no potential difference in this direction. Say this is y direction. Say in this direction, we don't have big changes. Therefore, the flow of water along the direction, along the length direction is negligible. So majority of seepage happens from this side to this side because there is a very big difference in the heights. Along this direction, there is not much flow. Not only that, the flow is also negligible. Also, the variation in the flow is also negligible. So under these assumptions, we considered the 2D version of the continuity equation. We are looking everything at a plane. So instead of considering the entire 3D object, we take a section of the dam like this. Let me use a different color. So you consider a section of a dam like this. Let us call this ABCD. And you analyze only this portion. So you assume that all the z components of velocity are 0, and the other components of velocity do not have any variation along the z direction. So the expected flow of water is just in plane. All the velocity of the water is planar. That is, the velocity doesn't have a z component, and Vx and Vy also do not depend on z. So if they don't depend on Z, all the Z, this term vanishes, and we have sorry, not Z. It depends. I mean, in the third direction, it doesn't vary. So if you take this as X and this as Z, typically in soil mechanics, we take Z positive downwards. Then Vy is equal to 0. It is assumed there is no flow in and out of the plane of paper. And also you assume Vx is a function only of X and Z, and Vz is a function only of X and Z. So all all Y derivatives vanish, and then we have the yeah, and then we have the planar equation, which is yes, yeah, partial Vx with respect to X plus partial Vz with respect to Z is equal to 0. So this is the continuity equation for 2D flow. And we can also have 1D flow. Suppose you have an aquifer, suppose you have a slope, or just take a laboratory case where you confine soil between two, you have a mass of soil, and suppose we maintain some head and steady flow. So again, the dominant flow is in this direction. The flow components, the velocity components in the cross section can be neglected. So we can also further reduce it to the case of 1D flow as partial Vx with respect to X equal to 0. So these are the various versions of continuity equation. This is the general 3D equation, but in civil we are mostly interested in 2D flow and 1D flow. Now the next part is how do we handle this? So this is the governing equation for the velocity vector. And one more thing I wanted to say. So I said it's the discharge velocity. So discharge velocity is defined for 1D flow. Suppose we have, let us have a mass of soil like this. We have a container filled with soil. To the left, we are maintaining a certain head. And to the right, we are having some other head. So there is a potential difference between the left and the right. Let us call this delta H. And let us assume all the pipe is frictionless. So let me use a different color. So only the pink portion is soil. And let us suppose there is a constant flow rate Q in and out of the. So there's a constant flow rate that is maintained, and this head difference is also maintained. Under these conditions, let the area of cross section of the soil be A and the length of the flow be L. Under these conditions, we define the discharge velocity. So it's a case of 1D flow, right? It is an assumption. There will always be some small velocity components in the Y, and suppose this is X direction, and Y and Z are like this. There will always be small components, but they are neglected. So it is 1D flow. And we define the discharge velocity as Vx is equal to Q by A. Now Vx is not the velocity of the fluid through velocity of water through the pores. And Vx is also not the velocity of water molecules. So it is neither of these. Vx is an average measure. So it is an average measure. Just like how we have it in the open channel flow. It's an average measure. You take the flow rate and divide by the area of cross section. That is the discharge velocity. And note that A is the total area, which includes area of the soil plus area of the voids. Now there is another related term called seepage velocity. Let us denote it as Vxs maybe. So Vxs is the velocity of water through the pores. Velocity of water through the pores. Now if you take a cross section, there will be soil. And we have the pores, and pores are filled with water. Now we know the porosity is volume of, say, if it is saturated volume of water by volume of the total volume. Now, if suppose you take the lengths to be same, if they are kind of prismatic, it's an approximation, it's not exact, then it is nothing but the area of water by area of the total area into length. Now again, by continuity, the total flow rate should not change. Now the discharge velocity into area should be equal to, we define the seepage velocity as the velocity of water through the pore. So that should be equal to the seepage velocity into area of water alone. But what is area of water? It is nothing but eta times the total area. Therefore, the seepage velocity is nothing but the discharge velocity divided by the porosity. So this is another important relationship. So whenever we say seepage velocity, the seepage velocity is the actual velocity of water through the pores, and that is much higher than the discharge velocity. You know, porosity lies between 0 and 1, typically around 0.3 or so. And so the seepage velocity, because the area of the pores is very small in compared to the total area, the actual velocity of water is much higher because it is scaled by this factor of the total area divided by area of water, which is the inverse of porosity. So the seepage velocity is related to the discharge velocity as by a factor of the 1 by porosity. So this is one thing. So is this enough? No. Now we'll see more. We'll see further. So this is the governing equation for the velocity. Now, how do we relate it to other variables in the problem? So we are trying to get the governing equation of flow through a porous medium. Flow through soil. No need. Flow through soil. Now, one governing equation is the continuity equation. Say, it is similar to equilibrium in our solid mechanics, right? So one equation is continuity equation, which says this one, right? Which is this. So if you're comfortable with the vector notation, it is the divergence of the discharge velocity equal to 0 under steady state seepage conditions. So this is the continuity equation. But how is the velocity related to pressures? Pressures are the other unknowns, right? So as we are dealing with laminar flow, let us use the heads. So another assumption is assuming laminar flow. So if you assume laminar flow, and let us consider the same example, we have this. We have a steady state. We have the steady state 1D seepage. And this can be easily measured. This is an experiment that can be easily carried out. And this is soil. And the head difference is say delta H. So we are assuming a steady state laminar flow. And not only that, we are also assuming that the velocity head is negligible. because of the high friction that occurs when water flows through soil, because soil particles, there are so many soil particles, the surface area is very large. If you consider pipe flow, this is water, and only this perimeter is wetted perimeter is only so much. But if you take soil particles, the wetted perimeter is very high, the friction is very high, therefore the velocity head. So if you write down the Bernoulli equation, Bernoulli equation is the total energy given by the pressure head P by gamma W plus the velocity head, which is V square by 2G, plus the elevation head, which is Z. This is equal to the total energy. This is the Bernoulli equation. Bernoulli equation for laminar, steady, inviscid, whatever, and along a streamline, right? So you can consider a streamline from here to here. You can consider a streamline from here to here. And as I said, because of the high friction, the velocity head can be neglected. The pressure head is given by the hydrostatic pressure. We are not supplying any pressure here. But this E is not a constant. As if you assume the pipes are frictionless, as water flows through the soil, as water flows through soil. So as water flows through the soil, it loses its energy because of friction. So due to friction, so if there are particles like this, water flows this way. And as it flows, due to the friction here, some amount of the energy is dissipated as heat. A part of the energy, so it may be heat, yeah. So due to friction, there is energy loss. So as water drags against the soil particles, this side, so there is some potential difference which is causing water flow in this direction. But these are soil particles and water is flowing through them. As the water layers drag against the particles, there is, right? If you rub your hands for some time, you generate heat. That is basically frictional dissipation. So some amount of the energy is lost, and uh, that is called the head loss, right? So if we have steady inviscid laminar flow along a streamline, what does it say? The Bernoulli equation says that this quantity is constant, E is conserved. But when we have frictional flow, E is not conserved, and we have what is called head loss. And so again, recall you are aware of this various types of head. One is so between two sections, suppose we have soil, and let us take this to be section A, this to be section B. The total head at section A is the elevation head, plus the pressure head plus the velocity head. And flow through soil, this can be neglected. And the total head at pressure B is the elevation head plus the pressure head plus the velocity head. If we have Bernoulli type flow, then it should be HA should be equal to HB. On the other hand, if suppose there is flow in this direction through soil particles, there is frictional dissipation. Therefore, HA is greater than HB. And the difference is called the head loss. The loss in total head is HA minus HB. So to relate the head loss to the velocity, we have what is called the Darcy's equation. So Darcy's equation or Darcy's law says that the discharge in 1D flow, Darcy's law holds for 1D flow. It says that the discharge velocity is proportional to the hydraulic gradient I. What is the hydraulic gradient? It is nothing but the loss of head per unit length of flow. So if the length is L and the loss of head as water flows from this place to this place is delta H. What is delta H? It is the loss of total head. Darcy's equation states that the discharge velocity of water as it flows through a permeable medium is proportional to the hydraulic gradient, which is the head loss per unit length of the flow. And the proportional constant is called the hydraulic conductivity or permeability. So V is equal to K delta H by L, where L is the length of the flow and delta H is the head loss. So this is called Darcy's law. Now you can just substitute in. So this is now let us take A and B infinitesimally close. Then what do we get? Suppose we take A and B infinitesimally close. This delta H by L, suppose L is very small, then delta H by L becomes partial H with respect to X. Right? Now we consider 1D flow. So, but in 3D flow, we can have different permeabilities in different directions. So we say Vx is by Darcy's equation in X direction, we get Kx partial H with respect to X. Vy is Ky partial H with respect to Y. And Vz is Kz partial H with respect to Z. Now we can substitute these into the continuity equation. Again, steady state. What did we have? Partial Vx with respect to X plus partial Vy with respect to Y plus partial Vz with respect to Z equal to 0. That was the continuity equation. Now, if you substitute all this, assuming Kx, Ky, Kz are material properties, it depends, assuming that they don't have, they're constant, they don't vary with X, Y, Z. They can be different in different directions. But if you take two different points, Kx, Ky, Kz are assumed to be the same. Although they don't have to be under realistic conditions, it's an assumption. So if Kx, Ky, Kz are assumed to be constant, then partial Vx with respect to X plus partial Vy with respect to Y plus partial Vz with respect to Z is nothing but Kx is taken as a constant, partial dou square H by dou X square plus Ky dou square H by dou Y square plus Kz dou square H by dou Z square is equal to 0. Now we have gone from having three variables. So Vx, Vy, Vz were three unknowns. But what has Darcy's law helped us? Darcy's law has converted one vector variable Vx, Vy, Vz into. So here Kx, Ky, Kz are material properties. We know them. X, Y, Z are just coordinates. And the only scalar unknown here is H, which is the potential or the total head. So H is the total head. One small thing here is you need to have a minus sign here, right? Because the head is lost. If you take it as HA minus HB, it is decreasing along positive x direction. So that is fine. So it is understood that right. This is fine. HA minus HB is fine, but this will be negative. So the partial H with respect to partial x is how much H increases with an increase in x, but delta H is actually a decrease in H with respect to L. So there's a minus sign here, which means the entire equation will have a minus. This is a minus, minus, minus. So that's an entire, this entire thing is multiplied by minus, but that doesn't matter because there's 0 on the right hand side. Now coming to, so this is the governing equation. Now coming to the case of 2D flow. If we have 2D flow, we have Kx dou square H by dou X square plus Kz dou square H by dou Z square equal to 0. This is important. Now, now here is the interesting thing. So if let us suppose that let us suppose the soil is isotropic. What does isotropic mean? Isotropic means that properties do not depend on the direction, which means Kx is equal to Ky is equal to some constant K. And that permeability is positive. So K is greater than 0. So you can cancel it out on both sides and you are left with dou square h by dou x square plus dou square h by dou y square is equal to 0. And what is this? This is the Laplace equation. This is the planar Laplacian. So this is the Laplace equation for the potential head. Now, to solve the Laplace equation, so the solutions of Laplace equation are called harmonic functions. The solutions of the Laplace equation are called harmonic functions. Right? So we have this dou by dou x of dou h by dou x plus dou by dou y of dou h by this is z, right? So this is z. Dou by dou z of dou h by dou z is equal to 0. This is the governing equation we have. Now look at it carefully. Look at it carefully. Suppose we think of a function, suppose we find a function psi, right? Suppose we find a function psi of x comma z such that that is so. Suppose we have dou h by dou x appearing in the first term. Let us say it is equal to some dou psi by dou z. And dou h by dou z appearing in the second term, let us say it is equal to some minus dou psi by dou x. Now, if you substitute this into this equation, dou h by dou x is what? Dou h by dou x is dou psi by dou z, and dou h by dou z is minus dou psi by dou x. If you substitute, if we are able to find such a function, then del square h equal to 0 is automatically satisfied. Right? So if you have such a function, then dou h by dou x is equal to right. If you are able to find such a function psi, then this equation is automatically satisfied. If psi and h are related by these relations, then this equation is automatically satisfied. Not only that, you also look at dou square psi. What is dou square psi? It is dou by dou x of dou psi by dou x plus dou by dou z of dou psi by dou z. What is this? Dou psi by dou x is what? Dou psi by dou x is minus dou h by dou z. So it is minus dou square h dou x dou z. And what is dou psi by dou z? It is dou h by dou x. So it is dou square h by dou x dou z. This is also automatically satisfied. So del square psi is also equal to 0. Now, if there is a function which obeys these conditions, then psi is said to be the conjugate harmonic function of of H. So H is called the potential function. And psi is called the stream function. They are conjugate to each other. If they are related by this, they are conjugate to each other. And not only that, it may seem little mathematical, but it will quickly become clear why it is useful for us as civil engineers, right? So suppose we have this. Suppose we plot. We have this. Suppose we have a dam like this, or let us just consider a sheet pipe. This is the headwater level. This is the tailwater level, and this is the ground level. So here the total head is so much, right? So at this point, you can use the Bernoulli equation, total head formula. Suppose the datum is somewhere here. Here the elevation head on both sides is the same. This is the elevation head plus rho GH, the weight of water above, divided by gamma W, which is rho G. So it is so much. Right? This is the total head. So suppose here the head is H1. And here the head is H2. Between here and here, there are, so the head has, the water flow is somewhere like this. And head is decreasing from H1 to H2. So we can, and how does the head vary? So here head is H1, here head is H2. And the distribution of head is in the soil mass is governed by the Laplace equation. So del square H equal to 0 is what governs the distribution, spatial distribution of the head. Now this is H1, this is H2. Now you can draw many more H, right? So you can draw other values. So this can be, say, H. Let us call this. Fine, this can be, say, H3, H4, H5, and so on. So it is such that H1 is greater than H3, greater than H4, greater than H5, greater than H2. So this line corresponds to H equal to H3. These are just the contours of the scalar function H. You know, H is a function of X and Y. You find all X and Y such that H of X comma Y is equal to H4. That is this contour. These lines are called equipotential lines. They're called equipotential lines. Why are they called equipotential lines? Because if you go along this line, what is the potential? It is H3. So this is an equipotential line. 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 Along that line, the head is constant. So what does it mean? Can there be any flow along this line?
No, sir.
No, because flow requires some loss in head. Flow through a permeable medium requires some loss in head. If you have to force water through soil particles, you need to do some work. Without that, flow cannot happen. So these along an equipotential line, flow is zero. That is one idea. So that is fine. Now let us consider a flow line, right? Let us consider what is called a flow line. So suppose there is a water, say this is a flow line. And this is kind of what is uh, the path taken by water, say something like that. It is the path taken by water molecule. Now to this line, what is so this the tangent to the curve at every point. So let us take a different. So the tangent to this curve at every point gives the velocity vector of the. Suppose this is the path taken by water molecules, the path taken by water. Then you draw a tangent to that path. What do you get? You get the velocity. So the x component, so if say this is the flow line, if you draw a tangent, what is the tangent? It is dz by dx. So a tangent is the same, it should be, it is nothing but vz by vx, right? So if this is a flow line, you draw a tangent to the flow line. The tangent, the slope of the tangent is dx dz. So if you consider a triangle like this is dz, this is dx. The slope of the tangent is dz dx. But what is the tangent to a flow line? The tangent to a flow line is the velocity vector. Now, if the velocity vector is like this, then it has components vx in the horizontal direction and vz in the vertical direction. So dz by dx is equal to vz by vx. What else? Vz and Vx are by Darcy's law, we have Vz is dou h by dou z, minus dou h by dou z, and this is minus dou h by dou x. Right? Let's go to the next page. But what is minus dou? You can cancel out the minus. So what is dou h by dou z? You can check here. Dou h by dou z is minus dou psi by dou x. Here it is minus dou psi by dou x, and dou h by dou x is dou psi by dou z. Now just rearrange it. By simple rearrangement, you get dx into dou psi by dou x is equal to minus dou psi by dou z into dz. Right? Cross multiply, you get this. And rearrange it, you get dou psi by dou x dx plus dou psi by dou z dz is equal to 0. Can you recognize what this is? Psi is a function of x and y. What is this? What is d psi? D psi is using the Taylor's, is a differential in psi, and using the Taylor's expansion, you can write this as dou psi by dou x. This is the first order differential in psi. X and z. Right? So this basically says d psi equal to 0. If the differential in the function psi is 0, it means psi is equal to constant. So what does this say? So this says that if you derive the velocities, if you derive the velocities, right? If you derive the discharge velocity vector as the gradient of a potential, which is h, and that potential is nothing but the total head at every point. So think of these as functions of two variables. You have a scalar potential, which is the total head at every point. So physically, it means that you take a manometer, you take a tube, and then take a point in soil and then plug it in. Right? You take this tube and plug it in and find out to what height the water rises there. So that varies at every point in the soil. Therefore, this height to which water rises at every point in soil is a function of x and y. So it is a scalar function of two variables. Now, if you define the discharge velocity as the gradient of dou h by dou x, so there is this constant of proportionality kx. Where is it? Yeah. So assuming isotropy and all, you have this kx dou h by dou x. So you're deriving it by your you're deriving the velocity by Darcy's law. And if you derive such a velocity, the velocity corresponds to the contours of the conjugate harmonic function. So psi is the conjugate harmonic function. Now we saw that. So what does it? Psi equal to constant corresponds to flow lines. Right. So remember, we considered a flow line, which is the path taken by a fluid. You draw a tangent to a flow line, it is the velocity vector of that velocity vector of the fluid at that point. But the tangent to the flow line by calculus is also dz by dx, which is the slope of the tangent. Slope of the tangent should be equal to, but the velocity is oriented in the same direction, so that is equal to vz by bx. Now we equated these two. When we equate these two, we are considering the tangent to a flow line. So flow lines correspond to psi equal to constant. The contours of the conjugate harmonic function are the flow lines, and the contours of the potential function are the equipotential lines. Now, these two are obviously orthogonal. As you can easily see, these two are orthogonal. Why? So you see this dz by dx is, if you take a flow line, dz by dx is this. And if you take an equipotential line, dz by dx is nothing but by partial h with respect to z, right? This you can see. dz by dx is, if you have an equipotential line where h is constant, then the tangent to that line is it is this dou h by dou x and dou h by dou z. So this is the slope of the tangent of an equipotential line, and the slope of the tangent of a flow line we already got, which is just a minute. So this is an equipotential line. This is a flow line. And suppose the flow line had a component like this. It means that along a flow line, psi is equal to constant. So if, and the velocity vectors are directed this way. But if this velocity has a component along the tangent to an equipotential line, then that violates Darcy's law, which means you have flow along the, so this is an equipotential line. This is a flow line. This is the tangent to the equipotential line at the point of intersection. This is the tangent to the flow line at the point of intersection. We have shown that the flow lines correspond to velocity, right? The flow lines correspond to the velocity. So if this has a component along the equipotential line, it means the head is not changing, but you have velocity in this direction. So therefore, these two are orthogonal. That can be proved by more rigorous mathematical way, but this is basically it. Now, given given all this, how do we estimate the discharge through? How do we estimate? Estimate the flow. A seepage, right? So now, so the idea is we have a dam, we have a sheet pipe. This is the headwater level. This is the tailwater level. And the soil stratum is here. So this is the ground level. So there is no head loss from here to here. The total head doesn't change. Only the pressure head and elevation head change individually, but the total head doesn't change as there is no flow. Given a situation like this, we can always construct a flow net, what is called a flow net. So this is the first flow line. This is the second, equipotential line. This is the second equipotential, third, fourth, fifth, and sixth. Draw the equipotential lines. Then also draw the flow lines. So this network of equipotential lines and flow lines is called a flow net. So this is, say, this is h equal to h1, h equal to h2. Sorry, this is in pink. And so on. And these are the flow lines. Psi equal to psi1, psi equal to psi2. And along the flow line, we have the velocity vector. A tangent to the flow line is the velocity vector. Now, if you consider a square enclosed by two flow lines and two equipotential lines, this is called a flow field. Now, if you look at a flow field, it is enclosed by two equipotential lines and two flow lines. And the flow is in this direction, right? So suppose the change in the potential is delta H. And the change in psi is delta psi. So this difference is delta psi. This is psi equal to psi1, this is psi equal to psi2. Now the discharge velocity at the center of this flow, this is a mass of soil, right? We have constructed a flow field by a network of equipotential lines and flow lines. And you consider an area of mass of soil enclosed by two equipotential lines and flow lines. Then the velocity at the center is given by what? It is just the discharge velocity at the center is nothing but, so this is psi equal to psi1. This is psi equal to psi2. So by Darcy's law, we know that the discharge, this is the length along the flow is also. So this is the change in, sorry. So this is not the physical distance. So this is, say, h equal to h1. This is h equal to h2. And the physical distance, let it be, say, L. And this distance, let it be A. So the difference in psi is nothing but the flow between these two. So this corresponds to some velocity. This corresponds to a different velocity. So the difference is nothing but the flow through this channel. And the discharge velocity is nothing but del psi by del the area, right? That's how we define the discharge velocity. So, but by Darcy's law, it is also equal to K times the hydraulic gradient. What is the gradient? It is change in the head divided by L. Now, the idea is if we construct the flow net such that A is approximately equal to L, then we have the net flow through this channel is nothing but K into the head loss between the two. Yeah. So this is the area between two flow lines, and there is water flowing all in between. So this is called a flow channel. And with the amount of water that flows through this flow channel is nothing but, if you consider two successive equipotential lines, by Darcy's law, it is nothing but the permeability multiplied by the head loss. But if you have n such fields, right? If you have n drops in the potential, if you have n drops, if the number of potential drops if you construct the flow net, so flow net is basically the intersection, the network of equipotential lines and flow lines. And if you have, so you can, the area enclosed by two flow lines and two equipotential lines is called a flow field. And in a flow field, this is the direction of the velocity vector. The the flow through this is given by k times delta h, which is the difference in potential between these two lines divided by the spatial distance between these two lines. So that is the discharge velocity at the center of this flow field. Further, multiply the discharge velocity by the area, we get the flow, which is delta q. And we are assuming it is 2D, so this area is nothing but A into 1. But if you construct the flow net such that this A is approximately equal to L, which means this flow field should be roughly square. If we construct the flow net in such a way, then, and suppose there are n number of potential drops, and these are flow channels, right? So let us also consider NF number of flow channels. In this case, the total flow, which is the total loss due to seepage from the dam, is from one channel it is delta Q, from n channel is delta F, delta Q times NF. But what is delta Q? It is K times delta H. What is delta H? Delta H is the loss per flow, loss between two successive equipotential lines. But there are n such drops, right? This is 1, 2, 3, 4, 5. In this case, the number of drops is 5. If the total difference, now let us say the total difference is capital delta H, then and there are n number of drops, so delta H is nothing but K, the total drop divided by the number of equipotential lines. So this is a simplified formula we use for solving seepage problems. So given a situation, given a dam or whatever, some a reservoir, some water retaining structure, construct a flow net such that the flow fields are approximately squares. Count the number of flow channels, which is the regions enclosed between two flow lines, and count the number of potential drops, which is the number of regions enclosed between two equipotential lines. Let them be ND and NF respectively. Then you compute the total flow as total loss due to seepage as NF into the permeability into delta H by NT. So this is the total loss from a dam. This concludes 2D seepage. So this is the end of, at least for the GATE syllabus, this is what is flow in 2D. This is the end of 2D flow. So we'll look at problems. We'll definitely look at some problems. Then, yeah. So maybe I think we'll. So there are ways to measure permeability in lab. There are these falling head permeability and constant head permeability tests, but it's time. So let's look at the problems first, and we can come back to. I'll complete the notes and then I'll upload it in the groups. That is better. So, but problems are important. So let us look at this. There are 3 soil specimens, each 150 mm long, 100 mm in diameter. They are placed in series under a constant head flow setup as shown. So this head difference between this point and this point is constant, which is 560 mm. And these soils are prevented from being, so there is flow like this that you can understand. So there is flow like this through the soil. And that flow rate is maintained constant. So we have a problem of steady state 1D seepage, which is the simplest case. Now you can also solve along with me. So if you have this, what is constant? When you have the flow rate is constant in time, but what else we can see? right, head is constant, but head is also constant in time. So along, let us consider these three different soils. Right? Let us assume the pipes are all frictionless. Here there is no head loss. Here there is no head loss. Here there is no head loss. Here. Now let this difference be H1. There is some loss. So if you draw, basically this shows the energy grade line. So if you say this is the energy grade line of, you remember this is the energy grade line. You can choose the datum wherever you want. Maybe this dotted line can serve as the datum. So at this point, what is the elevation head? Elevation head is minus something. Plus, what is the pressure head? Pressure head is the height of the water column above this point. So that comes up to be, so this is totally, from this datum, it is this total height minus this height. So this is the, and the velocity head is negligible. So this is the total head. Similarly, take this point, right? If you take this point, elevation head is the same for all the three, and the pressure head at this point is so much. So the total head is here. Similarly, at this point, the total head is here. Therefore, the total, this line which I have drawn in pink measures the energy grade line, total, the loss of the total head as the variation of the total head along the direction of flow. That is called the energy grade line, as you know from open channel notes. Now, the head, as water, up to this point, the head is the same. Right? Up to this point, head is the same. Let me use a different color. So here the head is so much. There is no flow here. Here it is flowing through soil, so there is loss. And it reaches this point. Again, here there is no loss. Here it is flowing through soil, so there is loss. It reaches this constant value. Again, here there is no loss. Again, as it flows through soil, there is some loss. Then again, it reaches the constant value. Now, I have drawn it as a straight line, but if you want to see why it's a straight line, look at the continuity equation. So in 1D, it is dou Vx by dou x is equal to 0. But what is dou Vx by dou x? It is minus of k dou square h by dou x square equal to 0. Now it is 1D, so it's only that h of x equal to x1 is equal to x h1, h of x equal to x2 is equal to h2. Suppose the head at this point and this point are known. This is h1, this is h2. If it is known, you can integrate this equation, right? If you integrate it once with respect to x, you get k, you can take it to the other side. You get dou h by dou x is equal to c1. And you integrate it again, you get h is equal to c1x plus c2. And you enforce these two boundary conditions to find what is c1 and c2, right? So that is basically this. So h varies. It means your h is linear in x. Therefore, along the direction of flow, the head drops linearly. The total head drops linearly. That is the idea. But in this problem, the variation itself is not important. We are only asked to find the last h. What is the last h? So if we call this as h1, this as h2, this height difference h is nothing but h3. Now, for all the three masses of soil, what is constant? The flow is constant. Head is not constant. So whatever water is coming here, whatever water is entering here, has to go out here. Similarly, whatever water is coming here has to go out here. There is no flow here. This is like a manometer. It is connected here, and water rises to some point and stops. These are very long, right? It doesn't flow out here. But here we have a flow out. Here, head is maintained and there is a constant flow. And whatever flow enters here, it has to go out. So Q is equal to, use Darcy's law, K1 times velocity. This is first part, discharge velocity. Discharge velocity is the first part. So it is K1 times I1. What is I1? Delta H1 by L1 multiplied by the area of the flow A1. But Q is also equal to K2 A2 L2, right? And Q is also equal to K3 delta H3 by L3 A3. So That is one thing. Then what else we know? The total head loss from here to here is happening only across the soil, not in the pipes. So the total head loss from here to here is delta H, which is given. And it should be the sum of the loss here plus the loss here plus the loss here. So delta H is equal to delta H1 plus delta H2 plus delta H3. Now rearrange this equation so that you get delta Hi. I'm just writing delta Hi is equal to Q times Li by Ai, and in the denominator you have Ki, right? So just sum them all. In this case, the length of the flow in each it is 150 mm, and the area is also constant. So L1 equal to L2 equal to L3 is equal to L, and A1 equal to A2 equal to A3 equal to A. Just take it as some number. Don't substitute because you will lose time in gate exam. Just treat it as some L and A. They'll eventually get cancelled. So what is delta H? It is Q by K1 into L by A plus Q by K2 into L by A plus Q by K3 into L by A. Now L by A is constant, therefore you can find the flow, right? This is given, LA is given, K1, K2, K3 are given, Q you can find. What is Q? It is, so if you take this commonly out, you get 1 by K1 plus 1 by K2 plus 1 by K3. This is on the right hand side. Now you're taking it to the left, so this entire thing inverse. And you have an L by A that becomes A by L delta H. This is the flow rate, but flow rate is not what is asked in the question. We want to find out H, but what is H? H is equal to delta H3, the head loss across the third sample, right? H is the head loss across the third sample, and delta H3 is what? Use this. Delta H3 is Q L3 by K3 A3. So it is Q L3 by A3 is nothing but L by A. Uh, so H3 is Q. L3 by A3 is nothing but L by A by K3. And what is Q? Q itself is 1 by K1 plus 1 by K2 plus 1 by K3 inverse into delta H into A by L. This we already have. Now multiply with this into 1 by K3 into L by A. So this L by A by L gets cancelled. So H is nothing but 1 by K1 plus 1 by K2 plus 1 by K3 inverse into 1 by K3 into delta H. That's all. Delta H is 560 mm. K1, K2, K3. So what is this? This is the harmonic mean. So the harmonic mean of K1, K2, K3. This is K3. So this you can just substitute. Now note, always be careful with the units. Delta H is in mm. K1, K2, K3 are given in centimeters per second. But in this particular problem, you see this has the dimensions of L and this has the dimensions of 1 by L. So these two will get cancelled. So you don't need to transform it to mm per second, and you don't need to waste time. You can directly substitute here, but always be careful. Now H is asked in mm, right? H is asked in mm. And if you substitute all these values, so K1 is whatever 0.001,003 and all that. If you substitute the values, you get B as 40 mm. Similarly, we'll look at the easy questions, then others will. So this is also simple, right? We have an anisotropic soil deposit, which has coefficient in vertical and horizontal directions as Kz and Kx respectively. For constructing a flow net, the horizontal dimension of the problem's geometry is transformed by multiplying factor of. So this is a conceptual question, but it's a 1 mark question in GATE. This is just something to remember. But how it comes is, if you remember, the actual continuity equation we had was Kx dou square h by dou x square plus Kz dou square h by dou z square is equal to 0. This is the actual continuity equation. But if the soil is isotropic, we say Kx equal to Kz and we cancel it on both sides and we got dou square h by dou the Laplacian. So if K is isotropic, I said this reduces to del square h equal to 0. But if these two coefficients are different, it doesn't reduce to that. So in that case, what people do is they transform the geometry. How do we transform the geometry? Let us see. So the horizontal, so the question says an anisotropic soil deposit has a coefficient of permeability in vertical and horizontal directions as Kz and Kx respectively. For constructing a flow net, the horizontal dimension of the problem's geometry, which means x, they are doing something to x so that this becomes Laplacian. Right? Make a transformation as x becomes some x dash such that this equation, which is a general second order PDE with constant coefficients, that becomes the Laplace equation. That is the idea. How do we do that? So it is transformed by multiplying factor of. So now let us look at it, right? Which means, so basically you're disturbing x and you're leaving z undisturbed. So let us divide throughout by kz. So it becomes kx by kz dou square h by dou x square plus no kz. It is just dou square h by dou z square equal to 0. Now this matches with the Laplacian. What is the Laplacian? It is dou square h by dou x square plus dou square h by dou z square equal to 0. This term doesn't match. So what they do, let us suppose you'd call x is equal to some, you do this change of variables, right? If you say x is equal to x dash times some multiplying factor r. If you do that, then dou h by dou x is what? Dou h by dou x is, by chain rule, dou h by dou x dash by dou x, right? Or yeah, fine. Let us do the reverse. Let us do a change of variables. X dash is equal to x times r. Then dou h by dou x is nothing but dou h by dou x dash by dou x by chain rule. Now let us substitute this dou h, this expression into this equation. So dou h by dou x, so dou h by dou x is dou h by dou x dash into dou x dash by dou x. But dou x dash we have taken it as r times x, which means dou x dash by dou x is nothing but r. So dou h by dou x is r times dou h by dou x dash. Next, dou square h by dou x square is differentiated once again. So what it is r times dou by dou x of dou h by dou x dash. Again, apply the chain rule. You get dou square h by dou x dash square into dou x dash by dou x, which means r square dou h by dou x. Now r is just a dou square h by dou x square, dou x dash square. Now r is a parameter that we have chosen. We have introduced. Why did we introduce? We want to transform this general linear second order PDE into the Laplace equation. Now just substitute into this. So we get kx by kz into r square dou square h by dou x dash square plus dou square h by dou z square equal to 0. Now if I choose r square to be kz by kx, then this becomes Laplace equation. So that is basically the transformation. So if you remember, x is equal to x dash is equal to r times x, and r is square root of kz by kx. So that is the question. If we have an anisotropic soil deposit, we cannot construct a flow net. We can construct a flow net only when we have a harmonic function and a conjugate harmonic function. But harmonic function and conjugate harmonic functions exist only as the solution to the Laplace equation, not for a general second order linear partial differential equation. So first you need to get harmonic and conjugate harmonic functions. In order to get conjugate harmonic and harmonic functions, you need to transform it to Laplace. For that, you're choosing a parameter R. You're choosing a transformation like this. It's just like integration. Well, integrating, you do a change of variables, right? Similarly, you do a change of variables. You consider a new variable x dash as R times x. You're scaling. What does this mean? The problems, the horizontal dimension, which is the x lengths, are scaled by a factor, which is the scaling factor R. How do we choose the scaling factor? You choose the scaling factor such that we get what we want, such that the equation transforms to Laplace equation. So for that, R square should be equal to kz by kx, which means R should be square root of kz by kx. So therefore, for constructing a flow net, you have to make this transformation x dash is equal to x into kz by kx. So the horizontal dimension of the problem's geometry is multiplied by square root of kz by kx. If they say it is divided by some, if it is a quotient of something, it is the inverse. So this you need to be careful. This is also simple. Again, this is another simple question. This also we can look at. So this is the piezometric surface, right? This is the piezometric surface. This is the reference datum. So this is the total head. Let this be H1, let this be H2. This is a direct application of Darcy's law. So looking at aquifer directly, don't get into this formula, right? So that's a common mistake. This formula you might learn. I'll derive and I'll put it, but this is something people remember this is a very commonly asked question. So this people try to remember, but this holds only when you're pumping water out of a borehole. This problem is different. You're not pumping anything. Sorry. We are making two boreholes, right? You're making two boreholes. This is an aquiclude. Aquiclude means it is a pervious layer sandwiched between two impervious layers. And the problem here is this water cannot enter this layer. So it is kind of compressed between the two. And if there is a head here, suppose it is a hilly region, water will flow from this side to the lower side. In the process, there is some head. The pressure, it is pressurized. The water in the aquifer is pressurized. So once you drill a borehole, automatically the water will rise to some point. And that is this. So this borehole acts as a piezometer. So this is the piezometric surface, which is also equal to the energy grade line. And if you assume this is 1D flow, we already proved that in 1D flow, the head drops linearly. So you can, so the hydraulic, this is the total head at point 1, this is the total head at point 2. Now we can find the discharge velocity. What is the discharge velocity? It is the permeability into I. I is constant because it is linear. So it is, what is the permeability? Permeability is 80 meters per day. So hydraulic conductivity is the other name for permeability. It's 80 meters per day into the hydraulic gradient. What is hydraulic gradient? Delta H by L. Now this is in meters, this is in meters, this is in meters. So you don't need to do anything to the units. Here it is meters gets cancelled. It is 55.2 minus 34.1 divided by 2500. So if you find out what this is around 0.6752 meters per day. This is the discharge velocity. Let me put a D here to denote it is discharge velocity. If the now this is the tricky part of the question. If the distance between the piezometers is 2500 meters, the time taken by water to travel through the aquifer from the piezometer location P to Q in days is what? So now you see the time taken by water to travel will depend on its actual velocity, not the discharge velocity. Discharge velocity is Q by A. If the net flow rate through a section is Q and you divide it by A, that is the discharge velocity. That is not taken, that is not the velocity of water through the pores. So if you have to find out what is the time taken by water to travel, that is usual distance by time type velocity. So that is the seepage velocity. That is the actual velocity of water through the pores. So as I said, seepage velocity is discharge velocity divided by the porosity. Now, what is the discharge velocity? It is 0.6752 meters per day. Porosity is a dimensionless number, 0.25. And the seepage velocity is something like 2.7008 meters per day. So the water is traveling 2.7008 meters per day, and the total distance is 2,500 meters. So how many days it will take? So the number of days it takes, so time is equal to length by the seepage velocity, not the discharge velocity. So length is 2,500 meters, and the velocity, the seepage velocity is 2.7008 meters per day. So if you compute this turns out around 900, and they're asking round off to one decimal place. So always compute to 2 or 3 decimal places and round off only in the last step. So the correct answer is 925.6 days. So this, I have checked the key. They accept any answer between 924 and 926. So this is a numerical type answer. The correct answer is this. So we are already past time. These are also simple questions I will solve, and I actually have to upload a lot of solved problems, right, for channel flow and this. I will do it by Wednesday, right? Tomorrow there is some work. I'll do it by Wednesday. By Wednesday, I will upload the solutions to written solutions to these, so it is helpful. And if you have any doubts, we can also look at the problems in the next class. So next we have to look at consolidation and shear strength. So nothing much changes. We'll start with the same continuity equation. To look at the time rate of consolidation, we retain the time derivative. And then it is actually simpler. There are a lot of empirical relations, so it is then it is mostly like a formula based questions. So that also we'll see in the next class. Any doubts?
No, sir. Thank you, sir.
Yeah, thank you. Sorry for the extra time, but it took some time. Maybe I'll finish the notes and I'll also upload the answers.